disconcerting. I'd have to point out that this is all mathematical and theoretically based. Okay, there isn't a shred of evidence to support this. But mathematically, it does make sense, and Einstein did say matter and energy are just for the same thing. There's the diffraction. Okay, so well, antelope being diffracted. Okay, I don't know if Americans see that or not. It wasn't until a couple of years later where a couple of guys were doing a little work for Bell Laboratories. I'm talking about Davison and Germer. Flip over to the next page. And they directed an electron beam and shot it toward a nickel crystal, and they obtained a diffraction pattern. Okay, did you hear what I said? I said they shot an electron beam and a nickel crystal, and they obtained a diffraction pattern. The electron. Well, look. If you were down at the end of the hallway, and you said, "Hey, Mrs. Sawan, you can't catch me," and I threw a ball at you, a baseball, and you saw it coming toward you, and you ran down towards Gillette's room, and you saw the ball stop toward the end of the hallway and go and turn or move around and start coming after you, yeah, that would be like, what the heck is that? I mean, matter's not supposed to behave that way. Okay, waves behave that way, but matter doesn't. Particles don't behave that way. And here we had matter, an electron, behaving exactly like that. We have a situation where the electron is actually showing wave-like behavior. Diffraction is clearly wave behavior. This was the first experimental evidence to support de Broglie's claim that, in fact, matter had a dual nature, that it could be wave-like in nature and at other times be particle-like in nature. And when we realized that, when we realized de Broglie was correct about that, I will tell you this, that changed everything. Because we started looking at the wave-like nature of matter, specifically the wave-like nature of electron. This aspect of studying the wave behavior of matter, we actually have a special branch of science it's called quantum mechanics. Quantum mechanics, or wave mechanics, deals with the wave-like, the study and the mathematics behind the study of the wave-like nature of matter. And ladies and gentlemen, I know you hold your cell phones near and dear to your heart. Okay, your DVD players, your TVs, your computers, none of that would be possible if it weren't for the fact that we understand the wave-like nature of the electron. The fact of the matter is, without that, there's no way we could do it. And since that time, we have learned that there are some really bizarre and weird things in our world. Our universe is a little bit different. The fact that electrons could behave as waves is very, very strange. We've actually went ahead and found out that, well, for instance, if you had a roller coaster car drawn like this, okay, so Joe, you'll have to draw this so she can see what I'm talking about. Okay, if you went off the edge, would you expect to be able to reach the other end? No, there's just no way because you don't have enough energy, right? Well, it turns out in our universe actually says that you can borrow energy that you don't have as long as you give it back within a certain time frame. So it is possible for you to actually tunnel through and actually appear on the other side so long as you give the energy required to do that back to the universe within a certain amount of time frame. Now, because Planck's constant is so small in our universe, the amount of time we're talking about is just too small a time for you personally to do that, which is why you can't walk through the wall. But electrons can do it. It's called quantum electron tunneling. And they can actually, it's not on the test, guys. This is not on the test. I'm just letting you know that there's some weird things that we can see happen. And electrons do this all the time. I mean, that's how we base our computers, is the fact that they have this ability to tunnel through energy barriers like that. We've seen some really weird stuff. They've actually done experiments where they took an atom, and using lasers, they were able to get the atom to go ahead and occupy two positions at the same time.
So what about conservation?
Well, that's it. The law of conservation of energy is not violated because of Planck's constant. Now, there's no way, thanks to the small value of Planck's constant, there's no way you're going to see me go zzz and have two Mr.Sawans. But we've done it with atoms. I mean, that's just bizarre. And this has led open to a variety of discoveries, including what we're going to see in a moment, a new model of the atom. But before we go there, I want to give you a practical application. I've already mentioned the fact that any basic electronic component, okay, our understanding of it and the ways it works and the reason why we've been able to capitalize on it has to do with us taking advantage of this wave-like nature of matter, specifically that of the electron. Probably a more useful way of seeing how we've taken advantage of the wave-like nature of the electron, though, would probably come and more easily understood in this regard, and that is in terms of the microscope. How many have heard of an electron microscope? Oh, so you've heard of the expression. Sometimes it's referred to as a scanning tunneling electron microscope. There's different types of electron microscopes. But so what the heck is an electron microscope? Well, some of you are involved in bio. Have you gotten into into microscopes yet?
Yes.
Okay, so you know what resolution is? Sure. Okay, for those of you not in honors bio yet right now, resolution refers to your ability to resolve, that is to tell the difference between 2 points. If you're magnifying something, you want to be able to distinguish between the 2 points. If you can't do that, if they look like 1 point, you're limited. Well, in order for you to be able to do that, to distinguish it, you've got to strike this, whatever you're looking at, with a wavelength that is shorter than the distance separating those 2 points. So for instance, if you use a wavelength like this, okay, of light, or light behaving as a wavelength, I should say, or behaving as a wave, as long as the wavelength itself is shorter than the distance between the 2 points, you'll be able to see those as 2 distinct points. If you illuminated whatever you were looking at, in this case here, with a wave that the wavelength was longer than the distance separated, if you try to illuminate, it would look like 1 point. You would not be able to distinguish between the two. We can sort of illustrate this. Yes, sir?
So blue light will have a better resolution than
Yes, blue light would give you better resolution than, say, something like red light. Perfect. Michael, you're dressed just for the occasion. Come on, man. Okay, what I would like you to do is I'm going to basically be sticking you. Don't worry, it won't hurt. I want to hold your arm out like this. Basic class. You're going to turn what I'm going to do is this, just to show you what we're going to do so you know it doesn't hurt, is I'm going to take these 2 paper clips and I'm going to basically stick you in different places and I'm going to come up and stick you in the same spot, okay? All right, so if you feel like it's in 2 different places, like, am I hitting you in the same spot?
No.
Okay, so you'll just say no, and then I'll say, what about now? And you'll say,
No.
okay, and you understand? And when I'm hitting you in the same spot, then I want you to say yes, okay? So look there you go. Okay, so here we go. All right.
No. 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 Yes.
Take a look.
No.
Okay, now, thank you.
You felt wrong.
Your ability to resolve that difference has to do with the density of your neurons, the nerves that are in your body has different concentrations. For instance, if we had done it on his lips, we would have had to get them right on top of each other before he would say, yeah, you're in the same spot. Or if we did it on the fingertips, their hands, okay? Do you think that was bad? If we did it on the back of his calf or on his back, we would have had him way far apart, and he would think that we're hitting the same spot. Okay, that's sort of what we mean when we talk about resolving ability in terms of being able to tell the difference between 2 points. You guys with me so far? All right. Well, this means we're limited to what we can magnify using visible light. Okay, Eric alluded to this already. Well, you mean that means that blue light would be better than red light? Yes, it would, because it has a shorter wavelength. But there comes a limit to which we would not be able to discern between 2 points, because if those 2 points are closer together than 400 nanometers, it's going to look the same. Of course, the solution to that would be to simply move to what? Ultraviolet and X-rays and gamma rays. We go to higher and higher frequencies. The problem is this: even though we have the technology for the device to look at an ultraviolet and then translate it into visible so we could see it, Okay, we could do that. The problem is, as you go to higher and higher frequencies, that is shorter wavelengths, you also are dealing with more and more what? What? Energy, that's right, Joe. You're going to be dealing with more energy, and that energy could have so much energy it could actually damage what you're trying to actually go ahead and look at. You see the problem? But we can take advantage of the electron. The electron can behave as a wave. And here's the cool thing. It's not a form of EMR. So its wave, the electron doesn't carry the same damaging energy that higher frequency EMR would have associated with it. And the wavelength for electron is far smaller than that of something, say, like a smaller than that of visible light. Consequently, we can actually take advantage of it, and this is what's responsible for things like this. Let me show you a couple little pictures taken with electron microscope. There it is. Okay, there's one little guy. Take a look at this little guy, isn't it? Look at the detail. Look at that detail. This was taken using an electron microscope. This is a picture of a common midge or gnat. Anyone who's played center field knows what I'm talking about. Those little things that, you know, that fly around. Yeah, that's this guy right here, okay? And you can just see the detail. There's no way you could get that with visible light. There's just no way you could get that amount of resolution. Now here's another picture. This picture was taken again, and what they did was they color enhanced it. What you're going to be looking at is a sewing needle. The sewing needle has been colored purple just so you could see what it looks like. And there's some little micro beasties at the bottom there. So the yellow that you see on the needle is bacteria. So you can see we've taken a picture of it. Yeah, and you can see the sewing needle at different resolutions and the bacteria on the sewing needle. And there's little micro beasties down here that are using this. Little micro beasties at the bottom. And again, you just do not get this. This is just a nice practical application of taking advantage of the wave-like nature of matter to get this kind of resolution. Now, I saw some of you looking at the little micro beasties I was pointing to at the bottom. Some of you I know might actually recognize these little guys. What are these little guys down here? What is it, Kyle? These are what dust mites are. These are dust mites. You see the little flakes right there? Okay, yeah, that's actually, you guys understand what dust is, right? 90% of dust is exfoliated skin, that's right. Yeah, and so this is actually skin cells, little pieces of skin tissue that have been exfoliated, sort of like taco chips from heaven as far as the dust mites are concerned. They just sit there and, you know, gnash away and eat at them. Of course, dust mites, if they're going to get a steady supply of exfoliated skin, I mean, you know, probably the best place to be would be where? Where you spend so much time. In your bed. So, yeah, in the room. Yeah, that's where these guys really like to hang out. Now, if you change your bed linens, you know, say once every week or once every 2 weeks, there's probably not that many in. Say maybe, I don't know, at most 20,000 or so. Now, if you don't change it but once a month, oh well, we're probably into the probably close to 1 million, maybe 2 million of these. Now, I know there's going to come a time when it's, you know, storming out, it's late at night, your parents went out for the night, and you're getting ready to go to bed, and you might be a little nervous. As you lay your head down on your pillow, don't be afraid. You're not alone. You have lots of little friends with you.
Yeah, I'm cool with that. Just breathe in.
Have you ever heard the expression, ignorance is